on congruence. So the idea is thinking about, for example, a 12-hour watch or a 12 clock. So we always talk about time in terms of numbers less than or equal to 12. So if it's 8 o'clock in 6 hours, if we're using just 12-hour time, we don't say that it's going to be 14 o'clock. We say it's 2 o'clock, since the final position of the hand will be at 2 on our clock. So 14 and 2, though, are in a sense kind of equivalent, or the same, representing the same type of number when we're working modulo 12. And so this is going to be the idea of working with congruence modulo some number. So let's back up a little bit and think about the division algorithm first. So this is the idea of long division when we first learned it back in grade school. So thinking about this formula, n is equal to q times m plus r. So what this is saying is that any number n can be expressed in the form q times m plus some remainder r. So n divided by m, you get some quotient q and a remainder r. The remainder must be positive, so it must be greater than or equal to 0 and less than the absolute value of m. So if r was bigger than m, then it means we could have had a larger quotient. So q is called the quotient, r is called the remainder. If the remainder is 0, then we say that n is divisible by m, or that m divides n. So let's look at some cases with different positives and negatives to see how this works. So for example, 512 for n, and m is equal to 17. So on your calculator, take 512, divide by 17, and see what the whole number part is. So you'll see that you have 30 point something on your calculator screen. So what this means is 512, the quotient is equal to 30, when we divide by 17, but there's some kind of remainder. To find out what that is, on your calculator, take 512 and subtract 30 times 17 to see what is left. You'll see that there is 2 left. So 30 times 17 is 510, plus 2 is 512. So in this case, our quotient q is 30, our remainder r is 2. If it's a negative 512 instead, let's think about how this changes. So when we take negative 512 divided by 17, we see the same thing that we saw on our calculator screen before. A negative, though, is in front of our 30. So if we were to do just negative 30 times 17, let's write this down and see what the problem is. Negative 30 times 17 is negative 510. So to get negative 512, we would have to subtract 2. But we said that the remainder had to be positive, so this is not possible. Instead, when we're working with a negative value like this, we're going to round down. So we're going to use negative 31 times 17. And then we can add 15 to get back up to negative 512. And so it's almost as if we go further into the negatives that we want, and then we can add a positive remainder to get back to where we want to be. So our q here is a negative 31. Our r is a positive 15. So r must always be positive. That's why we can't use negative 30 as our quotient. So what if the 512 is positive and the 17 is negative? Well, now we can do a negative 30 times a negative 17. This gets us our positive 510. And then adding 2. So our quotient can be negative. That's okay. So q is negative 30 and our r is a positive 2. So what if they're both negative? So this will be similar to what we saw in part B. We have our negative 5, let's try that again, negative 512. So we're going to need negative 31 times 17. And then we're going to again add times our, let's try this again. Scratch that, back up a step. So we're going to have positive 31, since our 17 is negative, times negative 17. This gives us a negative value that's more in the negatives than our negative 512. And then we can add 15. So since our 17 is negative, this time our 31 is positive. So our q is 31 positive, our r is 15 positive. So the positive 31 times negative 17 gives us a negative value, and then our positive remainder of 15. So let's do some definitions to go with this. So if m is an integer greater than 1, if x and y are integers, we say that x is congruent to y modulo m if x minus y is divisible by m. and this is the notation that we use. So x minus y is divisible by m. So let's think about some numbers that would be congruent to 3 modulo 10. So we need to make sure that when we take 3 minus this other number, it's something that's divisible by 10. Well, for one number, it's going to be congruent to itself, right? Because 3 minus 3 is 0. 0 is definitely divisible by 10. So then thinking about some more positives, we need to now have something that when we subtract, we get something that's a multiple of 10. So for example, 13. 13 minus 3 is 10. 10 is divisible by 10. So using that same pattern, if we had 23, 23 minus 3 is 20. 20 is divisible by 10. You can do 33 and 43 and so on. So now going the other direction, we need some number that when we take x minus y, 3 minus this number, that we end up with something divisible by 10 again. So what if we did a negative 7? So the 3 minus a negative 7 is 10, and then when we divide, we end up with a number divisible by 10. So then negative 17 and negative 27 would also work. Another way of thinking about it is that these numbers have the same remainder when divided by 10. And so if we were using our division algorithm from above, we would have 13 is equal to 1 times 10 plus 3. 23 is equal to 2 times 10 plus 3. 3 is equal to 0, 3 plus 3. So they all have the same remainder when divided by 10 when they're congruent modulo m. So let's think about whether or not each of these statements here at the bottom is true. Is 16 congruent to 10 mod 2? Well, we can check that 16 minus 10 is 6, and 6 is divisible by 2. 6 divisible by 2 is 6 divided by 2 is 3. So this is true. 16 and 10 are congruent mod 2. How about 49 and 32 mod 5? So if you take 49 minus 32, we get 17. Well, when you try to take 17 and divide by 5, it doesn't come out to be a whole number. So it goes in 3 and 2/5. It has some leftover stuff, right? That means that these numbers are not congruent mod 5. They don't have the same remainder when you divide by 5. About 30 and 345. So subtracting, it's okay if it's negative when we subtract. We get negative 315. When you take negative 315 and divide by 7, we get negative 45. So these two numbers are also congruent mod 7. So if two numbers are congruent, they have the same remainder when dividing by our m, our mod m, and also when we subtract, we should get a number that's divisible by m. So let's turn to the next page. So an example, all books for the past 50 years have had a number called an ISBN number that can be found on the book. There's two different types. We're going to talk about the 10-digit code. So this is a 10-digit code that's got 4 parts. One part tells you about the group, one about the publisher, a number assigned by the publisher, and then a check digit. Using the check digit allows publishers to detect an incorrect ISBN and not ship the wrong books or things like that, or check if there's an error in what they've received. The check digit has 11 possible values, the numbers 0 through 9, or an X, where X represents 10. Think about Roman numerals as how they decided on the X. So this digit is determined using this formula. You multiply the first 9 digits of the ISBN by 1098754332, add these 9 products together to get a number Y, and the check digit, we'll call it D, is chosen so that Y plus D is always congruent to 0 mod 11. So that means that Y plus D needs to be divisible by 11. So let's try this out for the book Marley and Me. So we have all of the numbers except for the check digit. We're trying to figure out what number the check digit should be. So we want to start by multiplying by 10 times the first. So we're going to have 10 times 0, 9 times 0, plus 8 times 6, plus 5 times 0, 7 times 0, plus 6 times 8, plus 5 times 1, plus 4 times 7, plus 3 times 0 plus 2 times 8. So a lot of these are 0, so a lot of these drop out. We end up with 145. So we need to make sure that 145 plus the check digit D is congruent to 0 mod 11. So trying to think about numbers close to 145 that are divisible by 11. So 154 is a multiple of 11. So 154 is congruent to 0 mod 11. So you can check 154 is divisible by 11. So that means our number D, 154 minus 145, needs to be equal to 9. So 154 minus 0 is 154. 154 divided by 11 gives us 14. So now 145 plus 9 gives us that 154 that we need. So the check digit for this particular book would be equal to 9. That number guarantees that there hasn't been an error in the other numbers that have been sent. So if they go through and they try this code with these numbers and it doesn't match up with the check digit, they know there's some kind of problem with the ISBN that has been sent. So it's an error detecting code. We spent a lot of time in section 2.2 talking about the idea of equivalence relations, and it turns out that congruence is actually an equivalence relation. So let's look at this in example number 5. So let's let our set A be the set of integers. And here's how we're defining our relation. So AB is in our relation if A is congruent to B mod 2. So we want to show that congruence mod 2 is an equivalence relation. So we've got 3 things to look at. Let's start with reflexive. So we know that A is going to be congruent to itself mod 2 for any A because A minus A equals 0 and 0 is divisible by 2. So it is reflexive. So any number is going to be congruent to itself, mod 2, because the difference between A and A is always going to be 0. So is it symmetric? Well, let's think about this. If A is congruent to B, mod 2, then a way of thinking about this is that then A and B yield the same remainder when divided by 2. Well, if they yield the same remainder when divided by 2, that means that B is also congruent to A mod 2. So switching the order there doesn't change what we're saying. Saying A is congruent to B or B is congruent to A, same idea. So this one is symmetric. So A minus B, if that's divisible by 2, B minus A also still divisible by 2. So how about transitive? So the assumptions for transitive, we start out with if A is congruent to B and B is congruent to C, both mod 2. Well, this is saying that A and B give the same remainder when divided by 2, and this is saying that B and C give the same remainder when dividing by 2. Well, the remainder you get for B didn't change, so if A and B have the same remainder, then B and C have the same remainder as A and B. So then A, B, and C yield the same remainder when divided by 2. So A must be congruent to C mod 2 if they have the same remainder when divided by 2. So therefore, congruence mod 2 is an equivalence relation because it satisfies the 3 properties.